Well, hello, calculus students and seekers of truth. In this lesson, we are going to study logistic equations and logistic functions from the perspective of differential equations. Now, ultimately, our goal is to understand these equations and be able to solve a problem similar to this one. But we're actually going to start with some basic principles, and we're going to try to understand a little bit more about what a logistic function is, first by comparing them to exponential functions. All right, so let's contrast the exponential function. So an exponential function, we know it takes this format, dp dt, the derivative with respect to time is linear to the population itself. Now I'm using p here as a variable for population because that's the most common, but exponential functions could apply in many other different types of situations. All right, and we also know that when we are done solving this equation, we are going to get something like p of t is equal to some constant times e to the kt. Okay, we also know that exponential functions have a graph that resembles something like this. Okay. We can shift it up, we can move it around, we can flip it, and just some other characteristics here. And it's just this is a little bit of review, and it'll help us to compare to logistics. It is always increasing. Or always decreasing. So if I were to flip this function over the t-axis, it would be always decreasing. And this is my way of saying there can be no extrema. There can be no possible way for this function to have a maximum or a minimum. It's always increasing or it's always decreasing. And the concavity, notice here the concavity never changes. So an exponential function is either going to be always concave up or always concave down, and it's very nice in that sense. The reason that you have this derivative being linear to the population is, if you think of it in practical terms, if there's a greater population, then they multiply quicker, they multiply more, and so they grow quicker, which then increases the population, which then increases the growth rate, which then increases the population, and on we go. Okay, so some nice characteristics there of an exponential function. Now, the downside of using exponential functions is they don't really model what happens in the real world. In any population, whether you're talking about bacteria or rabbits or people or deer, eventually the growth slows down. Okay? And we need a function that is a little bit better in order for us to handle the real world situations. All right, so by contrast, a logistic function takes a slightly different format. It's dp dt is equal to kp, okay, where k is some sort of constant, times 1 minus p divided by k. All right. I made a little bit error. This shouldn't be the same letter. I'm going to change this to an r instead of a k. Okay, so we have two different constants. There's one r, that's called the growth rate, and k, that is called the carrying capacity. Okay. So r is the growth rate, and k is the carrying capacity. Now, we are absolutely going to solve this differential equation, just not right now, not in this lesson, because it requires a lot of dense and complicated algebra, and we're not quite ready yet for that type of work. So I'm going to kind of skip to the end here a little bit and show you what the final equation would be like if we were to derive it. So it would be p of t equals capital K over 1 plus some constant of integration e to the negative rt. Okay? So we solve this differential equation up here, we end up with this function right here. And there's a few important features here that if we were to take the limit as t approaches infinity, then this part right here would go down to 0 or almost 0, and what would we get would be k, right? So what does this mean graphically? Well, graphically it would look somewhat like this. So here's t, here's p, and you would have a flat line here, exponential growth, and then there would be a leveling off. Okay? And where is this horizontal asymptote? It is at k, or the carrying capacity. Okay? Okay, so if we look at this now, we can see that there's some features to this graph as well. This is also always increasing or always decreasing. Okay. So if I were to flip this over the t-axis, do a vertical reflection, it could be always decreasing. Okay. Now, this is the more common case, is the increasing type. We rarely see logistic decay, but it does exist. We just rarely ever use it. And the other feature here of a logistic function is that there is a change in concavity. Okay, so there is a change in concavity. In other words, there is such a thing as a point of inflection. Okay, and we'll talk a little bit more about what that means. All right, so now let us return to our example. Let's work through the specifics of it, and then we're going to kind of jump back and forth between the theoretical and the practical here.